So this is the second part of 9.1. We're going to talk about series. And last time we talked about, we came up with this idea of sequences. We worked with sequences. We said sequences were functions where our domain was positive integers. So we're just plugging in 1, 2, 3 to get some list of numbers. With series, we're adding together the terms of the sequence. So the difference between a sequence and a series is with a series, we're adding the terms together. So sequence is just a list of numbers. A series, we end up adding them together. And the way we write that, the symbol we use, is we call it a summation notation or sigma notation. And the reason we call it sigma, we use this capital Greek letter sigma. Sigma means sum. And let me draw that a little neater. So that's our sigma. And the way we do it is I equals, usually equals 1 to some number of a sub I. And this just tells me to add up all the terms of my series for I equals 1 to n, whatever my number is. We call I is the index. And it just tells us how we add the numbers together. And 1 for this one is our lower limit. And n is the upper limit. So the sigma tells us we're adding these things together, and we're starting at 1, and we're adding all the terms from 1 to n together. And we'll do a couple of examples in just a second. I just want to give us some properties of sums that we can use as we're doing our work with this. So our properties of sums, if we multiply, if we're summing if we're multiplying each term by a constant, we can pull the constant out front. So if we have some constant that's multiplying each term of our sequence, we can pull that constant out front. And our other property that we'll use is if we're summing two sequences that are added together. So if we have two things that we're adding together, we can split those into two pieces. So if inside our sum we have something, two terms that we're adding or subtracting, we can split that into two series. Questions on this so far?
Can you just keep it up for a second?
Sure.
So
When are we going to use this? Well, we'll do a couple of examples today where we'll work with these. But later we'll talk about what we call arithmetic series and geometric series. Geometric series, we can look at, we can sometimes model population growth with a geometric series. An arithmetic series, we can model certain kinds of interest. So it's anytime you're adding things together and you're starting with 1, 2, 3, and we're just adding a whole bunch together, that's when we're going to use a series. All right, are we good on this? So let's look at a couple of examples of using sigma notation or summation notation. So we want to find the sum. So our first sum is the sum of I equals 1 to 4 of 3i. So I have a constant here. Using our properties, I could write this as 3 times the sum I equals 1 to 4 of I. And all this is telling me to do is 3 times, for I equals 1, I get 1. For I equals 2, I get 2. For I equals 3, I get 3. And for I equals 4, I get 4. So I'm just putting the numbers from 1 to 4 in, writing the terms of a sequence, and adding them all together. And this is 3 times 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. So that sum is 30. If I had the sum, let's do one that's just a little more complicated. And before I do this, anybody have any questions about what I did here? Now, if we had our sum the sum of 4i plus 2, for I equals 1 to 4, I'm just substituting from I equals 1 to 4, substituting that in and adding each term together. So for I equals 1, I get 4 times 1 is 4, plus 2 is 6. When I equals 2, 2 times 4 is 8, plus 2 is 10. When I equals 3, 3 times 4 is 12, plus 2 is 14. And when I equals 4, 4 times 4 is 16, plus 2 is 18. And then I can add all of these together to find my sum. So this is all summation notation is telling me to do. Take each term, add them together. Does that make sense? Let's look at one that's just a little more complicated, just to see how we work with the summation notation. If we want to find the sum I equals I equals 1 to 5 of minus 1 to the, we want to do I minus 1 times I factorial. So I'm just substituting the numbers from 1 to 5 into this expression and adding each of those terms together. So for I equals 1, I get negative 1 to 0 times 1 factorial plus negative 1. For I equals 2, I get 2 minus 1 is 1 times 2 factorial plus negative 1 if I equals 3, 3 minus 1 is 2 times 3 factorial plus negative 1 to the 4 times 4 factorial. And finally, we're summing from I equals 1 to 5 plus negative 1. This should be 3, sorry. Negative 1 to the 4th times 5 factorial. And if I write each of those terms out, I get negative 1 to the 0 is 1, and 1 factorial is 1, so that's 1, plus negative 1 to the 1 is minus 1, so I have a minus sign here. 2 factorial is just 2. Negative 1 squared is positive 1, times 3 factorial is 6. Negative 1 to the 3rd is minus 1, and 4 factorial is 24. And minus 1 to the 4th is positive again, and 5 factorial is 120. So my signs alternate, add all these together, and if I add all those together, I get 101. So I'm just adding my terms. Questions on that? So essentially with summation notation, we're just taking the terms of our series and adding them all together. Whatever this series is, we're just adding the terms that our index tells us, from the lower limit to the upper limit. Yes?
Why did you do 0 for the first one, not 1? Because isn't it I equals 1?
I minus 1 to the I minus 1. So if I is 1, 1 minus 1 is 0.
Okay.
Minus 1 to the 0, any number to the 0 power is always 1.
So why did you put? Because it's 0 because you plug in 1 for I and 1 minus 1. Oh.
Right.
Okay.
So I plug in 1 for I here, so my exponent is 0.
You ended on 4.
Okay. Does that make sense now? Okay, good. All right, last topic for today. Infinite series. This is when things start getting interesting. So an infinite series means, all this means is that we're summing from 1 to infinity. So my upper limit is infinity. And the reason, one reason that infinite series are interesting is that depending on our terms, when we add up all the terms, all those infinite terms, sometimes we get a finite number. A geometric series is one example, and we'll talk about those a little bit in the next couple lessons. Yeah, Kelsey.
Why is the lower limit 1 instead of 0?
It doesn't have to be 1. That's just what, usually we're going to use 1.
Okay.
But remember we defined our sequences, that the sequences were functions whose domain was the positive integers, and positive integers start with 1. So we're kind of staying consistent with that. Yeah, Alex.
I had a question. Well, I was in an example, one of these they have a lower limit as 0, and they put it in a factorial. Is 0 factorial 1?
0 factorial is defined as 1.
Okay.
Yes.
Because 1 factorial is 1.
Yeah. So yeah, 0 factorial we defined as 1, and that's just by convention to make things work out nicely. So if we sum from 1 to infinity, we have an infinite series. We could sum from 0 to infinity, and certain types of series we will sum from 0 to infinity. Just for now, we'll keep our lower limit as 1. So anytime our upper limit is infinite, we have an infinite series. If we have an infinite series and we only want to add a certain number of terms, we call the summation from I equals 1 to n of a sub n. We call it the nth partial sum. So if we have an infinite series and we're only looking at a certain number of the terms, we call that a partial sum because we're only adding up part of it. So the partial sum is not any different from what we just did before, except that the partial sum is a part of an infinite series. So when you see partial sum, it just means your series is an infinite series and we're only adding together a certain number of the terms. And when we're looking at an infinite series, the infinite series wants you to add the entire series together. And we'll figure out some ways to do that in the next couple of lessons. But an nth partial sum just means you add up a certain number of terms. So if you're looking at the fifth partial sum, for example, you would say n equals 5 and add up the first 5 terms like we did on our previous examples. Now what I think is cool application of infinite series and partial sums is they let us write any repeating decimal as a fraction. We can figure out what fraction a repeating decimal represents a repeating decimal. So let me do a quick example of that. You have a couple of these in your homework assignment. So I just wanted to go through this. So let's say we have the sum from n equals 1 to infinity of 3 times 1/10 to the nth power. And we want the sum. Now we can't start writing down numbers and add up all those infinite numbers together, but what we can do is look at the partial sums and see if we see a pattern. So we're going to look at the partial sums for a pattern. So we're just going to start writing down some terms of this series. So I'm going to say that the sum n equals 1 to infinity of 3 times 1/10 to the n. So we're just going to start with n equals 1. So if n equals 1, 1/10 to the first power is just 1/10. Times 3 is 3/10. So that would be my first partial sum. My second partial sum would be 3 times, we're going to add 3 times 1/10 squared. And my third term would be 3 times 1/10 to the third. And we just keep adding these fractions. Well, let's rewrite these and see if we can figure out a pattern. This is the same as 3/10 plus 1/10 squared is what? What is 1/10 squared? 1/100th times 3 is 3 over 100. 1/10 to the third is 1 over 1,000 times 3 is 3 over 1,000. I'm going to rewrite these as decimals. 3 divided by 10 is 0.3, plus 3 divided by 100 is 0.03, plus 3 divided by 1,000 is 0.003. And I keep adding these. If I add these together, I get 0.333 ... What is 0.333 ... 1/3. So we know that we just get a 3 at the end over and over and over again. So this fraction is 1/3. We'll do more with this later. All right, our homework. I know, you're welcome. I know you're in a hurry to get to your next class. There you go. And we'll work more with infinite series a little later.